Hello, everyone. My name is Matt Pahachik. I'm a doctor of physical therapy with GL Rehabilitation Services, and I am the founder and I run the program called Aging Gracefully. Today, I want to take you behind the scenes and show you how I built something and I'm really proud of, and it's completely free, interactive muscle anatomy and exercise research platform on our aginggracefully102.com or AG102 digital health platform. This is the story about what happens when you combine clinical expertise and AI tools and the honesty reality of how much iteration it takes to build something like this. It wasn't magic. It was 13, 16 many rounds back and forth, catching mistakes, correcting anatomy, and refining until we got it right. So let me walk you through the whole process. So why did I build this? If you've ever had tried to find a good muscle education resource online, you know the problem. The academic resources are great, but they're written for clinicians. My 72-year-old patients aren't really reading journal articles about EMG activation percentages. The consumer resources are oversimplified. They tell you to do squats for your legs, but they do not tell you which muscles are working, how hard, and what the research says. And the really good tools, they're behind paywalls. Anatomy apps cost money. Personal training costs money. Physical therapy costs money. Everything costs money. Our mission with Aging Gracefully has always been that financial circumstances should never limit our ability to access fitness education. So we set out to build something that covers every muscle in the body, all 116 of them. And that's not all of them, but those are the main ones with a lot of the EMG research behind it. These are going to be all exercise ranks for having the EMG studies and an interactive body chart where you can click on the muscles and learn all about it. And it had to be completely free. And so I did it all myself with AI. Because I know I couldn't do it by myself. I have no coding experience whatsoever. Here's how the workflow actually worked. There are three players in the process. First, Claude Chat. That is the Anthropic's AI assistant. This is where the research happened, where I planned content, reviewed quality, wrote the specific prompts, and would guide the code generation. We had over 20 separate conversations across this project. Second, Claude Code. This is the coding tool that actually written and executed all the Python and JavaScript code. It generated the SVG anatomy files, written the muscle path coordinates, built the skeleton system. We went through 16 different rounds and show you what those will look like in a little bit. And third, this is the part where people miss when they talk about AI, is the clinical review. Me. As a DPT, I looked at every single output and saying that muscle is attached in the wrong bone, or that fiber direction is the wrong direction. And I might have made mistakes, but we reviewed over 70 screenshots, which is crazy. And the AI generated the code. My clinical knowledge determined if it was correct or not. That distinction matters. Phase one was the research. We compiled EMG, or that is the electromyography research for all the 106 muscles of the bodies that we identified to be the most important. We organized them into 11 batches. We started with the gluteal and hip muscles, glute max, glute med, glute minimus, piriformis, the deep rotators. Then we moved on to the quads and the hamstrings, hip flexors, the adductors, calves, core muscles, the entire shoulder complex, upper arm, chest and back, foot and ankle, and all the remaining muscles. The last batch was the pelvic floor, which was particularly important for our aging adults. About 50% of women over the age of 65 and 25% of men over 65 experience incontinence. So we called, so we created sex-specific deep dives with different anatomy views, different exercise cues, and different clinical considerations for each. Each batch produced a comprehensive Excel worksheet. Let me show you what actually is in each muscle deep dive. Every single muscle gets 6 sections. First, the anatomy, origin, insertion, innervation, primary action, then specifically how this muscle is relevant for the aging adults. Not just what it does, but what it matters for independence. The second tier of EMG research, we organize the evidence from systematic reviews at the top, down through randomized controlled trials to individual studies. Every citation includes the actual percentage of maximum voluntary isometric contraction. This is the gold standard for measuring how hard a muscle is working during an exercise. Third, exercise ranking. Based on the EMG data, which exercise activates this muscle the most? This is what participants actually care about. What should I do to strengthen this? Fourth, we created a data quality rating system. Some muscles, like the glute max, have excellent research, 5 stars, multiple systematic reviews. Other muscles, like the obturator externus, has almost nothing, 1 star. Reliance on cadaver studies were transparent about what we know and what we do not know. Fifth, the aging specific notes. How does this muscle change with age? What's the fall prevention relevance? Are the independent thresholds? And sixth, clinical warnings, red flags, contraindications, when to refer to a specialist, because this education is not treatment. It's never treatment. It's all about education. We want people to know when they need professional help. Phase 2 is where things got really interesting and really challenging. We had this research data, but we needed a way for people to explore it visually. We wanted someone to be able to look at the human body, click on a muscle, and instantaneously see all the research we've compiled. That meant building interactive anatomy charts, 7 different views of the body, each with clickable muscle paths, different frontal, intermediate, superficial, deep, back views with superficial, intermediate, deep, plus the pelvic floor. And there's a male and female variants. There's 106 muscle paths, all generated from one code, all generated from code, all clickable, all connected to our research database. 102 individual muscle paths. Some of them we are kind of joined together, so that's why there's a difference between 106 versus 102 muscle paths. Here's the breakthrough. For all the 7 views, there's the frontal, superficial. Superficial had 24 muscles. These are the ones you can see from the outside: the pecs, the delts, the bicep, quads, abdominals, abs. The intermedius has 8 muscles underneath, the pec minors, adductors, VMO. The deep had 28 muscles, including the iliopsoas, the diaphragm, with lots of little foot and hand muscles. On the back, 11 muscles on the superficial. The intermediate had 9, and then the deep had 21. The pelvic floor also had its own sex toggle, so you can change between female and male, because they're distinct different anatomies, and we need to know them. So the femur was the difficult one. I could not figure out how the heck to get it right. So I had to use a reference image to make sure the code knew exactly what the shape should look like, with where the head of the femur should be attached, where the graciocanthor is, and where is the shaft and the distal end of the femur. So I ended up using a reference image, and that helped kind of give the AI a little bit more information. But then I have to be very specific how I describe the reference image as well. But it was a very testing my patience problem to figure out how to get this right. Then here's the honest reality of what that looked like. 16 rounds of iterations, not because the AA failed, because the building accuracy anatomy is generally hard. And the feedback loop between generating code and review and output clinically takes multiple passes. Round 1 and 2 were just getting the basics right. The first outputs were dark backgrounds. Muscles were outlines and not filled in. No skeleton underneath. We had to be extremely specific about what we wanted visually. Round 3 was a breakthrough. We added skeleton base layer and created anatomical landmarks with about 150 body constraints. That meant every muscle could reference real bone positions. Round 4 and 5 were all about proportions and detail. Wider stance, arms and abduction are a little bit farther away from the body. Hand and foot detail, joint continuation, so muscles connect smoothly across the joints. Tendon tapering at all the extremities. Round 6, the muscle fiber directions, making sure the striations on these muscles match the actual directions of the muscle contractions. Vertical for rectus abdominis, diagonal for the obliques, fan shapes for the pecs. There's 59 unique fiber angles across the 106 muscles. Now, these next ones were a grind. From 7 through 16, it was tough. So first, the comprehensive audit, we went through every view and found muscles that were floating in space, not attached to bones. We had to fix the pelvic shape, the femur angle, add pelvis floor views from both sexes, and then we had to debug a few things. There were some pixel shifts and starting to read the CVG outputs coordinates, calculating the exact gap between the different muscles on target bones. It was closing to be very nice to be precise. Reference images were needed to help a little bit, but each round taught us something about how to work with AI more effectively. Let me highlight 4 technical innovations that made this work. First, the anatomy landmark system. We defined about 50 body constraints, a skull center, shoulder joints, hip joints, knee centers, ankle positions based on 8 head anatomical models on the 800 to 1600 pixel canvas. Every muscle referenced these landmarks. If we moved the shoulder position, every muscle attached would move with it. Second, the skeleton architect. The bones rendered as the base layer, then the muscles rendered on top. This reinforced the most important rule: nothing floats. Every muscle path must touch a bone at its origin and insertion end. If it doesn't, it's wrong, and we fix it. Third, the fiber striation engine. Each muscle direction hatch lines that match the actual contraction axis. It isn't cosmetic. It helps learners understand which directions the muscle pulls. Vertical fibers mean the muscles pull vertically. Diagonal means it pulls diagonally. There's 59 unique fiber orientations for this. And fourth, the read then fix debugging approach. We developed around 11. Instead of guessing the pixel correlations, Quad Code reads the actual SVG outputs extracts the coordinates of every muscle endpoint, calculates the exact distance to the nearest bone, and reports any gap larger than a 15 pixel. Then we close that gap precisely. This is the methodology breakthrough that we finally solved the persistent floating muscle problems. So that's everything. We have a lot of great features into uh, this this website. We have seven reviews with different depths. We have different ways you can click on the muscle, get a full research, get the tailored EMG data, get exercise progressions, and more importantly, having like any clinical warning signs as well. So this process was a blast to make, and it was really rewarding to see it come to fruition. Here's what the difference looks like. On the left is what we started with. It was very early aspects. We just had dark features. It was that took a while to figure out how to do, and I just feel like it was not quite good enough. And I didn't want to just settle for this. I want to be a little bit more uh, precise, even though the image right now is not the best. And there's definitely better models out there, but every single change we did between these results a clinical correction. Each muscle is moved, attached to different bones. The fiber orientation was correct. This is what collaboration with AI actually looks like. It's not ask once, get it perfect. It's iteration, refinement, guided by clinical expertise. And then let me put some numbers behind this project. 106 muscles researched with EMG data, 11 Excel workbooks produced, 8 CVG anatomy files generated, 7 body views, plus the male and pelvic floor variant, 16 rounds of iteration between the cloud code, and the clinical review, over 20 conversations per over 80 screenshots, and clinical review and correction over all of them. The muscle database alone is 502 kilobytes of structured JSON files, origin insertions, innovations, primary actions, functional relevance, EMG data research, citations, and data quality ratings for every single muscle. And at no cost to participants, $0. That's the number one thing I'm proud of. We can make this be free for everybody. So what did I learn using AI as a clinical collaborator? First, and I cannot stress this enough, AI does not replace clinical judgment. It amplifies it. Every muscle placement, every fiber direction, every anatomical correction in this project required my training as a DBT. This AI generated the code brilliantly, but it had no way of knowing what the femur neck looked like, if it was wrong, if there was wrong direction, until I looked at it and said, nope, that's not how the femur looks. The domain expertise is the irreplaceable. Second iteration is a process, not a failure. 16 rounds sounds like a lot, but each round produced better anatomy, the willingness to look at the output honestly and say, that's not quite right yet. And the thing is yet. I would not give up. This is what drove the quality. If I had accepted round 2 output, we would have floating muscles with no skeleton, no dark backgrounds. Quality takes passes. Thirdly, specificity beats generality in every case. Early on, I'd say things like, make the adductors connect to the femur. That's too vague. The eye would shift a few pixels and call it done. When we started saying the adductor brevis inserts on the proximal lineal aspera on the femur at approximately x equals this, and x equals 320, y equals 508, things got fixed really fast. The more precise the input, the more the better the output is. And fourth, verifying the output does not verify verify the output always. Do not trust the process. Uh, the breakthroughs in round 11 was when we stopped assuming the corrections were applied correctly. So I would give it like you have to change this, and then it found out it wasn't actually doing it, and started reading the SVG files accordance to verify trust measurements, not assumptions. This is good clinical practice, and it's good work for AI too. So where do we go from here? Phase 3 is deploying this on the website aginggracefully102.com. The interactive SVGs will be embedded so you can click on any muscle and immediately see the EMG data, top exercises, and aging relevance. That's coming soon. Phase 3 is connecting the muscle data to the composite health score. So the AG102 scoring system, and that tracks the 5 pillars: cardiovascular, strength, mobility, stability, and power. Specific muscle assessments will feed into these pillar scores. And phase 5, we're going to have the community layer. We're going to gamify muscle challenges, exercise tracking tied to what muscle you need to focus on throughout the year. And all of this is evidence-based and is designed to help people age gracefully and maintain their independence. I'll leave you with this. Financial situations should never limit access to fitness education. That's the core belief behind everything I do with Aging Gracefully. The EMG research, the interactive body charts, the exercise progressions, all of this is available at no cost because that's how it should be. If you're interested in learning more at aginggracefully101.com, that is where I kind of connect all of my Aging Gracefully classes together, and then I built this aginggracefully102.com. This is the digital health tracking platform. You can reach me at 101aginggracefully@gmail.com. If you're a clinician or a developer thinking about using AI on your own projects, I hope this behind the scene was helpful. The tools are powerful, but the clinical expertise is what makes them useful. Thank you for watching. I'll leave you with this. Financial situations should never limit access